Hi everyone, in this presentation video, I will talk on securing the persistent state in intermittent computing. I am Hafiz Asad, recently graduated from Uppsala University, and I work with Luca Mottola and Timo Voigt, affiliated with Research Institutes of Sweden and Uppsala University, Erik from KTH Sweden, and Naveed Anwar Bhatti from Air University, Pakistan. I start off the presentation with the question that why do we need to secure the persistent state in intermittent computing? To answer this question, I will begin with the basic concept of intermittent computing, followed by the existing security threats against persistent state and the challenges in securing the persistent state. As you are aware that in energy harvesting devices, the energy is buffered in the capacitor. So once enough energy is buffered, the microcontroller starts performing the computations. However, these devices face power failures whenever the energy is insufficient. As a result, the program state is lost, and when again the energy is available, the device reboots but starts the computations from the beginning. Operating systems lacks the supports for providing directives to respond to a pending power failure. This hinders the forward progress. Therefore, to ensure forward progress, state-of-the-art intermittent computing solutions employ either a form of checkpointing or task-based programming abstractions. Both approaches fully or partially preserve the system state onto the non-volatile memory before the power failure. After getting power again, the device starts by restoring the previous state, after which it resumes the computation and repeats the cycle. However, the persistent state stored on non-volatile memory may include critical information on operating system and network stack configurations, as well as application data. This is vulnerable to a variety of security threats. Krishnan showed that while the device is off, recharging energy buffers, there can be three types of attacks. Firstly, an attacker can possibly exploit the debug port interface of the microcontroller to read or steal data, which not only raises concern regarding application and device security, but also about the privacy of the data which may be collected through environment using sensors. Secondly, an adversary can tamper the stored state to take control over the embedded system after the power is restored. Thirdly, the adversary could collect and execute previous stored states to repeat the execution order. This shows the need for securing the persistent state. However, securing persistent state incurs an overhead. It is also challenging due to extreme low availability of energy on constrained energy harvesting devices, especially at the time of persisting the state before the power failure. In our work, we experimentally applied different security mechanisms to measure and compare their security overhead, both in terms of energy consumption and execution time. This allowed us to assess the impact of the corresponding overhead on typical intermittent computing workloads. The applied security mechanisms include software and hardware implementations of encryption algorithms. Additionally, we explored the use of new ARM Trust Zone Protection Mechanism, which is Trusted Execution Environment for microcontrollers, and was previously available only in application processors. We considered four workloads: a simple bit counting procedure performed over 2048 random bits, an implementation of Dijkstra's shortest path algorithm fed with a graph of 128 nodes and 512 edges, an implementation of fast Fourier transformation over 128 complex numbers, and an implementation of the quicksort algorithm operating on an array of 256 elements. Of course, when it comes to securing persistent state, there could be many different attacks. Here we consider two different threat models. If we consider that the attacker has physical access to the device and may snoop or spoof persistent data on non-volatile memory and assume that the keys and tags are stored in a secure key area instead of a plain non-volatile memory, then we consider AES hardware and software security mechanisms. To secure persistent state, we selected AES encryption algorithm as it is an industry standard being widely used. It can be implemented both in software or with dedicated hardware support. For hardware-based implementation, we used embedded crypto accelerators inside the microcontrollers. For software-based implementation, we selected two existing well-known cryptographic libraries, Mbed TLS and Wolfcrypt. Both of the libraries are designed to provide lightweight, high-quality security software for constrained embedded IoT devices. On the other hand, if we consider debug port is not vulnerable, otherwise attackers may read and tamper checkpointing data, and consider that the adversary has the ability to run malicious code on the device by installing it remotely, and assume that the attackers may read the normal world memory, then we considered trust zone. The trust zone technology provides hardware isolation between memory, peripherals, and CPU resources by creating two separate domains, secure and non-secure, to protect data from software attacks. We use the secure domain for persisting the data. Please note here that the checkpoints are not encrypted when using the trust zone, which only protects the persistent data from malicious software accesses. For our experiments, we selected two ultra-low power ARM-based microcontrollers from Microchip, namely SAM-L11 Cortex-M23 as shown in left figure, and SAM-L21 Cortex-M0 Plus as shown in right figure, and we used their respective boards for the measurements. Due to the energy figures, both microcontrollers are credible targets for energy harvesting devices. The benchmarks were executed directly on bare metal without the operating system support. The Cortex-M23 features trust zone technology and a basic crypto accelerator supporting AES electronic cipher mode, whereas SAM-L21 Cortex-M0 Plus is equipped with an advanced crypto accelerator supporting AES, CBC, and GLOIS counter operating modes. Now, let's look at results obtained from the experiments performed and see the impact of security on typical intermittent computing applications with a 60 microfarad capacitor. These figures shows the experimental results of both microcontrollers. With a small capacitor of 60 microfarad, as shown in both figures, the bit counting procedure fails most often regardless of the security mechanism and sometimes even in the case of no security. This is because the capacitor is too small to accumulate sufficient energy to perform some application processing, execute security mechanism if any, and write on flash in a single power cycle. If you look at the left figure, that is the case of the Cortex-M0 Plus, for the other workloads, only the crypto accelerator makes it possible to complete the workload with the given energy budget. Moreover, the overhead imposed by the crypto accelerator compared to the case of no security is roughly comparable to the cost of application processing. In the case of Cortex-M23, only the internal crypto accelerator and trust zone make it possible to apply some security mechanism within the given energy budget and also complete the workload. Moreover, in the case of trust zone, the overhead is marginal as compared with the no security. Next, we analyze the overall trend of energy consumption and execution time in performing a checkpoint and restoring operation for a given amount of data. The trend for restoring is similar to checkpointing, therefore I'm discussing the checkpointing case. This figure shows the trend in the case of energy consumption and checkpointing operation on Cortex-M0 Plus with the advanced AES encryption modes. One can also look up the size of the checkpoint and find how much energy overhead will security impose in their system or application. The top lines with yellow and green colors are illustrating checkpointing with software-based AES securities. On the other hand, red and blue lines are illustrating checkpointing with crypto accelerator using 128-bit long and 256-bit long keys. Overall, it can be seen that the software-based securities has higher energy overhead as compared to checkpointing with hardware-based security and without any security. Moreover, the measurements also indicate two important observations. Firstly, using the crypto accelerator, the energy cost of running AES 128 or AES 256 is basically the same. Second, a marked gap also exists between the two software implementations we test. Mbed TLS outperforming Wolfcrypt on the Cortex M0 Plus. So if hardware support is not available, the choice of an efficient software implementation becomes crucial depending on the platform. This figure shows the trend in the case of energy consumption and checkpointing operation on Cortex M23 with the trust zone and basic ES encryption mode experiments. Here, the blue line is representing trust zone and black line is illustrating checkpointing without any security. It can be seen that trust zone has a negligible overhead. Moreover, the graph is also showing the results for AES securities which are not directly comparable with the trust zone. This indicates that the trust zone must be preferred to secure the persistent state whenever it's available and depending on the threat model. Well, attacks against the AES encryption also exist. Past studies indicate that the side channel attacks are effective against the encryption algorithms to retrieve the keys. To counter side channel based attacks, the internal crypto accelerator of Cortex M0 Plus features countermeasures, which were disabled in the previous experiments. So we measure the impact of enabling the countermeasures in terms of energy and time overhead. In the figures, it can be seen that the performance is only marginally affected, both in the case of energy and time. This figure reveals how varying compiler configuration and microcontroller clock settings impact energy consumption and execution time on the Cortex M0 Plus, using either software implementation of AES, the onboard crypto accelerator, or no security mechanism. The bars are stacked. The lower section represents encryption. On top of that is decryption. Similarly, flash write and then flash read is stacked. The top left figure shows the case of the crypto accelerator. The energy cost is dominated by flash operations, as it is also the case when using no security mechanism. On the other hand, when using software implementations of AES, the overall energy consumption is evenly split between running the encryption algorithm and flash operations, and remains largely the same regardless of the compiler configuration and microcontroller clock settings. This figure offers a complementary view, where the impact of running the microcontroller at high clock speeds becomes apparent, and yet causes no additional energy consumption as discussed earlier. The performance is almost unaltered depending on compiler configuration, which we ultimately conclude to bear no significant impact. In conclusion, we presented experimental results on applying different security mechanisms to protect persistent state in intermittent computing, including software and hardware-based implementations of AES encryption and ARM trust zone, using modern microcontrollers of the Cortex-M series. We found that the modularity and ease of update of software implementations comes at the cost of a marked energy and time overhead, which possibly prevents forward progress. The hardware-based implementations has a lower energy and time overhead, but require care in understanding their internals and their potential influence on performance. TrustZone, which is right now available on only a few platforms, shows almost negligible overhead, but at the cost of a different memory management scheme. Thank you very much for watching the video and for your patience.